In this video, we're going to be expanding on our knowledge of the solubility product constant, which is simply KEQ, but for dissociation and precipitation reactions, in order to calculate the molar solubility of a given ionic substance. Molar solubility, if you recall, is simply the maximum amount of a specific solute that is able to dissolve per liter of solvent. We can express this in terms of a concentration. So what we're looking for is the maximum concentration of solute expressed in the unit for concentration, moles of solute per liter of solvent, that occurs specifically at the saturation point. Remember that the saturation point is of interest to us because it is the first time when equilibrium occurs within a dissociation precipitation reaction. So if we consider the dissolving and precipitation of silver chloride, the equilibrium that we're going to end up with is solid AgCl is in equilibrium with Ag plus and Cl minus. And from this, we can construct a fairly simple KSP expression where KSP, the equilibrium constant for this dissociation precipitation reaction, is equal to the concentration of Ag plus times the concentration of Cl minus. Now, in order to calculate any ion concentration, we actually need a number for what the equilibrium constant is, and we can find that from a data table that looks like this. This is a solubility product constant data table that lists the KSP values of a number of compounds, all with very low solubilities at a specific temperature, in this case 25 degrees Celsius. So if we scroll down to the silver section, we can see that the KSP for silver chloride is 1.8 times 10 to the negative 10. So if we go back, we can write in that number as a reference point for us. Now, one of the confusions when calculating molar solubility is that what we're looking for is the concentration of a solute, but our solute in undissociated form is written as a solid. So why is this the case? Well, in every dissociation reaction, we can actually break it into two different steps. The first of which, where we go from the solid form of our precipitate simply to the aqueous form. Now, this step is not normally talked about because as long as we have an ionic solute, these two ions are not going to stay together permanently because water is going to use its polarity in order to pull the ions apart using ion dipole attractions. And for that reason, we actually get a separate dissociation reaction here where the two ions separate. So here we would actually write out that AgClAq separates into Ag plus and Cl minus. Now, the reason why we don't normally consider the first step is if we remember how elementary processes work, whenever we have an element or compound that is a reactant in one step and a product in the next step, we can cancel it and it therefore doesn't appear in the overall reaction. However, the first step tells us something very important. If we consider the mole ratio between AgCl, the temporary intermediate form of our solute, and the separate ions, we see that the mole ratio is 1 to 1 to 1. What this means is that even if we don't have any AgCl aqueous, any aqueous form of the two ions together in solution, we know that its concentration will be equal to the concentration of Ag plus and of Cl minus. And therefore, if we set this problem up as a rice table, we can find out what the relationship here is. If we're assuming that we're taking a specific mass of AgCl and dropping it into pure water, if it's pure water that we're starting with, then that means our initial concentrations of each ion are going to be 0 moles per liter, meaning that there is going to be no precipitation reaction, and the dissociation is the only reaction that will happen. Since the mole ratio is 1 to 1 to 1, that means that the magnitude and direction of change for each of the ions is going to be plus X, meaning that the equilibrium concentrations of Ag plus and Cl minus will both be X, meaning that if we calculate X, we will also find the concentration of AgCl that actually dissolved, and this is the molar solubility that we are looking for, even if the ions do not stay together permanently. So the calculation here is actually fairly straightforward. So if we remember what our KSP value is, 1.8 times 10 to the negative 10, we know that this is equal to the concentration of Ag plus times the concentration of Cl minus, and we know from this fairly simple Rice table that each of these is going to be X, which simply means that our KSP is equal to X squared, meaning that X is simply the square root of 1.8 times 10 to the negative 10 moles of AgCl per liter, and that's how we calculate molar solubility. Remember, of course, that this concept of molar solubility doesn't really exist permanently, because what we're more interested in are the concentration of each of the ions, but because of the mole ratio, it would be the same. A better, more practical question is finding out what mass of solute can dissolve if given a specific volume of water, and here's where we can use our solubility in order to determine this. So if we take our molar solubility, the value of X that we calculated, we start with the square root of 1.8 times 10 to the negative 10 moles of AgCl per liter, and if we want to find the mass of AgCl that is able to dissolve in a specific volume, well, we can take this volume and multiply it by our solubility in order to find the number of moles of solute that can dissolve. Remember that this is in milliliters, so we would multiply by 0.1500 liters instead. So now we have the number of moles of AgCl, meaning that all we need to do is multiply by the molar mass of silver chloride. I'm going to assume that you know how to look up molar masses on the periodic table. So molar mass of silver is 107.87. Molar mass of chlorine is 35.45. And if we work through some quick arithmetic here, we find that the molar mass of silver chloride is 143.32 grams per mole. And if we multiply by this final number here and put everything into our calculator, we'll find that we are able to dissolve 2.9 times 10 to the negative 4 grams of silver chloride in 150 milliliters of water. This is less than 1/10 of 1% of a gram. So this is why we say that compounds that have a KSP value have a low solubility, because almost none of it dissolves before we get a precipitate. In the next video, we're going to be analyzing trends of solubility and how solubility changes depending on what the state of matter of the solute is and depending on how temperature changes.